Welcome to this course Physics of Semiconductors, and I will start the lecture with an demonstration, an experiment that you must have done, you must have seen during your primary classes or upper primary classes, and the experiment is right here on the table, which looks for which of the materials are electrically conducting and which of the materials do not conduct. So, look at that experiment once again. So, we have a battery and a bulb, and these two hooks you can see. This is a series connection. We have just connected this battery to the bulb, and then one end of this bulb goes here and the open end of the battery goes here. There are wires here. So, you just connected a battery with this bulb, and the connections are open, and this acts like a switch. If I can connect it by an electrically conducting material, then the circuit is complete, the bulb should glow, and if I connect it by a material which is non-conducting, then it should not glow. That is our class 5 demonstration. So, let us see. I have a cycle spoke here, so it is a metallic object, and if I use this to connect these 2 points, you can see that the bulb glows. Okay? So, cycle spoke is conducting, is made of conducting material. Then I have a plastic coated copper wire. This is a usual copper wire which is used in our electrical connections, and on that we have this plastic cover. So, we have removed this plastic cover at the ends. So, if I use this copper wire to connect these 2 points, we again see that the bulb glows. So, copper is conducting, but this cover, plastic cover itself, here is that plastic cover alone. There is no copper wire inside, we have removed that, and this plastic cover, if I connect this, the bulb does not glow, and we say that this plastic is not conducting electricity, it is a poor conductor or an insulator. Okay, this is an insulator, but copper is a conductor. Varieties of things people put here, pencil lead, graphite and other things, and check what is conducting and what is not conducting. So, this primary school experiment just divides the materials in 2 categories, electrically conducting and then electrically non-conducting, which you can call insulators. But all conducting things are not equally conducting. All our circuits, all our household wiring, the motor of a fan, winding of this motor, all this is done with copper. Okay. One can do it with other metals also, they also conduct, but then copper is a much better conductor than aluminum. Aluminum is a better conductor than iron, iron is a better conductor than stainless steel, and so on. So, different materials have different conductivities. So, there is a gradation, it is not just a binary type conducting and non-conducting. So, I will give you some conductivities to give you an idea in what range conductivities vary. So, electrical conductivity, the SI unit is known as Siemens per meter. Don't worry if you do not understand what this Siemens per meter is, what this conductivity is, how it is defined. Maybe we will do it later in later lectures, but here just to compare, SI unit is given this S by M, and the numbers, you focus on the numbers to get a relative ideas. that which one is more conducting, which one is less conducting, and so on. So focus on those numbers only. So silver, so let's start with silver. The silver conductivity is 6.30 into 10 power 7 in this SI unit. Copper is 5.96 times 10 to the power 7. So if you can do a silver wiring in your house, that will be much more efficient as far as the electric conduction is concerned. Of course, the costs will be, you will be at the top of the world. Then you have aluminium. Let us see aluminium. Aluminium, the conductivity is 3.5 times 10 to the power 7. So this is 6.30, this is 3.5. So aluminium is not that costly, but then yes, the conductivity is lower. Iron is 1.0 into 10 power 7, even lower. Stainless steel, this conductivity is 1.45 into 10 power 6. And then silicon, the conductivity is 1.56 into 10 power minus 3. Germanium, it is 2.17, just 2.17. Then you have diamond. Let us write here. Diamond. Diamond, it is 10 power minus 21. Then glass, this is 10 power minus 11. And you have Teflon. Workers who work at very high voltages, their instruments are coated by Teflon, and the conductivity is of the order 10 power minus 23. So that's the kind of variation, and what we are interested in this course, the course is physics of semiconductors. And semiconductors, we are here, we are in this range. You can see if you compare with copper, copper conductivity is 10 power 7, 5.96 into 10 power 7, and silicon conductivity is 1.56 into 10 power minus 3. So almost 10 to the power 11 times smaller than silver. So this is silicon. Most of our course will take silicon as the model semiconductor. Germanium is there, then other semiconductors are there, gallium arsenide based semiconductors are very important. But of this range, so almost 10 to the power 8, 10 to the power 10, 10 to the power 11 times smaller conductivity than copper or aluminium or metals. But if you compare with Teflon, if you compare with glass, if you compare with diamond, plastics, this conductivity is much higher. Therefore, they are called semiconductors. And why we are focusing on semiconductors so much? Because semiconductors are almost at the center of our modern life. You think of ISRO sending 104 satellites in one go. All that control systems of these kind of things, the semiconductor is the one material which is there in all kinds of control systems. Chandrayaan, Mangalyaan, all those things, it's all because of this semiconductor electronics that we are able to do all these things. If we come to our own daily life, our mobile phones, our calculators, our televisions, TV sets, all these, or transmission, reception, all these things need electronics, and in those electronics we use semiconducting materials. Solar panels, you must have seen so many solar panels. This is seen as a great opportunity to fight this power failure situation or power crisis. So solar panels are there, lamps are there, small lamps are there which have small solar panels. You have big solar panels from where the electricity is given to the grids. Then the LEDs, light emitting diodes, they are called LED bulbs. All these LED bulbs are getting popularized, and so because they consume less power and all those things. So all this controls, wherever you have some control there, the semiconductors will be there in your washing machine, everywhere semiconductors. Therefore, we focus not on conductors, that's a separate physics of, in this course I am talking, not on insulators, but on these semiconductors. So what is this which makes semiconductors so important? What is this that gives copper a much larger conductivity than aluminium and much larger conductivity than iron? So how this conductivity is governed, what physics goes on inside the material which decides that this material should have this much of conductivity and so on. That will be the main thing that I will be doing in this particular course. So what I am focusing it is the mechanism of electrical conduction. Once I know the mechanism, then I will be able to understand what is making conductivity of the order of 10 power 7 or 10 to the power 6 or 10 to the power minus 3 or 10 power minus 11 and that. To understand that mechanism, I have to understand how electrons behave in a solid. So in a solid you have positive ions and electrons, or nucleus and electrons. Many of the electrons are in the inner orbits, and some of the electrons which are in the outer orbits, they actually decide many of the properties. So how electrons behave in presence of that multitude of those positive ions, that I have to understand. And very interestingly, that behavior of electrons in the field of positive ions or electric field, that is not governed by the classical physics that we learn in our high school days. Newton's laws of motion, F is equal to ma, and from that conservation of linear momentum, conservation of energy, all those things that we study, they are extremely useful equations, extremely useful procedures. But when it comes to understanding the motion of electron, the behavior of electron, how electron will respond in a given situation, these laws do not work, and we have to learn a completely new kind of physics which we call quantum physics, quantum mechanics. The application goes, and then all those things we call quantum physics, but the basic theory is quantum mechanics. So little bit of that quantum mechanics is needed to understand behavior of electrons in a solid. To give you a flavor of this or importance of this quantum physics, Let me talk of little bit of our sun. You know, we get all the energy on this earth from the sun. The life exists because we are getting so much of energy from the sun, and that energy is produced at the core of the sun. So what is there? Everyone knows in class 8, 9 we all study this, that you have a lot of hydrogen in the core of this sun. In fact, the entire sun is just hydrogen, and in the core you have hydrogen at very high temperature and high density, and that is being converted every moment into helium. And when hydrogen is being converted into helium, is combining the hydrogen atoms, ions, which are protons in fact, because hydrogen has only one electron, and at high temperature that electron goes away. So you have protons, and these protons combine to form a bigger nucleus, a helium nucleus, and during this, when it makes a bigger nucleus, energy is released, and it is this energy which finally comes to our earth. So let us do some little calculation using our Newton's laws and classical physics equations to see if these protons at that temperature are able to come so close so that they can form a nucleus. Okay, so let me do some calculations for that. So inside the sun, at the core of the sun, temperature is about 1.5 into 10 to the power 7 Kelvin. So that's the kind of temperature. At this temperature you have lots of protons and electrons and all those things, and the protons come together to form this helium nucleus only because of the random thermal speeds. Okay, so in the first phase, you know, two protons come together, they make a nucleus, a proton is converted into neutron, and then a deuteron is formed. That's the first step of this reaction. So proton plus proton, that makes a deuteron, which is the nucleus of hydrogen with one proton and one neutron, and then this proton is converted into neutron. So some positron and some neutrino, these small particles are created. The important part is two protons must form a nucleus of these one neutron and one proton and one neutron. So that's the kind of nucleus is to be formed. And when this nucleus is formed, what is the size of this nucleus? The size of this nucleus will be almost say 1 femtometer or so. You know, femtometer, 10 power minus 15 meters is called femtometers. So the size of nucleus is typically of that order. Even the big nuclei, uranium and all those things, they will also have a size of some 5, 6, 7 femtometers, not more than that. And why it is that? Why nuclei are of that small size? Because the nuclear force which keeps this nucleus as one unit bound, that is a very short range force. The nuclear force falls to almost zero once the separation between two particles, two protons or two neutrons, or one proton, one neutron, which we call nucleon. Okay, so proton or neutron, the common name is nucleon. So when two nucleons are, let us say, at separation more than 10 femtometers, the nuclear force is absolutely negligible, and therefore the nucleus is formed only in that range where the separations are femtometers type. So these two protons must come close enough, say at a separation of a femtometer or so, so that they can form this nucleus. So this is important. These two protons should come close enough so that separation between them is something like this. Now let us say, at this temperature, At this temperature, all protons are moving here and there, random velocities. Let us say there is a proton, and in a very favorite situation, this is going this way, this is going this way, so that they are trying to come close enough to each other. If the directions are different, then anyway the chances are even less. What is the speed? What is the average speed of this proton at this temperature? So for that you must be knowing from kinetic theory of gases that the average kinetic energy of a gas molecule is of the order 3/2 kT. What is K? This K is called Boltzmann constant. Now at this temperature, what is the value of this kT? This kT at this temperature, kT turns out to be about 1.3 kilo electron volt. Okay, you know kilo is 10 power 3 and electron volt is a unit of energy. 1 electron volt is 1.6 into 10 power minus 19 joules. So 3/2 kT is so this is going with 3/2 kT, this is going with 3/2 kT. So what is the total kinetic energy? Total kinetic energy, these two protons, total kinetic energy of these two protons, this will be 3 times kT. So this is 3 times kT and this is 3 into 1.3 kilo electron volt, which is 3.9 kilo electron volts. Okay, so this is the kinetic energy here. The separation is large, so electrostatic potential energy you can take very small, almost 0. Okay, how do you write electrostatic potential energy? This was kinetic energy, and the potential energy that is written as 2 protons. So charges are E and E. Q1 is E, Q2 is E. So Q1, Q2 over 4 pi epsilon naught R. This is the potential energy, and to start with, when they are approaching each other but still at a somewhat large distance, this you can take as almost 0. Now as they come closer, their speed will decrease because they are repelling each other. Remember, this is a proton, this is a proton, so they are repelling each other. The speed will decrease. They are coming closer. R is becoming smaller and smaller. So the potential energy is increasing. Right? So the potential energy is increasing, the kinetic energy is decreasing, and our classical mechanics based on Newton's law tells me that kinetic energy plus potential energy should remain constant. So that total mechanical energy to start with is 3.9 keV. So that should remain 3.9 keV. The kinetic energy will decrease, potential energy will increase. What happens? Is it the case where the protons are slowing down, and at some place the speed becomes 0? So let's see. If that be the case, I should get a value of this separation R, where this entire kinetic energy is converted into potential energy. And if I try to calculate that R, if I get that R, then yes, sure, and if I see that no, that R is negative or some unphysical, then we will say that no, they are going and almost colliding with each other. So let's look at that situation where these two protons have come close enough here, and at this time the kinetic energy becomes 0 at some separation R. Okay, for that what should be the thing? It should be 3.9 keV. The total mechanical energy should be equal to E square over 4 pi epsilon naught and then R. And this quantity is a fixed quantity. This is electronic charge, 1.6 into 10 power minus 19 coulomb. 4 pi epsilon naught or epsilon naught is a fixed quantity. And if I calculate this entire thing, this E square over 4 pi epsilon naught in proper units, this turns out to be 1.44 EV/Nm. Very useful relation. This electronic charge E square over 4 pi epsilon naught, you can write in SI units and you will get all those things, but you convert in this unit. This is EV and this is Nm. Nm is nanometers. Okay, Nm is nanometers. 10 to the power minus 9 meter is called a nanometer. So electron volt unit and then nanometer unit, 1.44 EV/Nm. This is this part, and then it is R here. So from here you can calculate what is R. R will be equal to 1.44 EV/Nm divided by 3.9 kilo electron volt, and if you calculate that, it turns out to be almost 400 femtometers. So as the separation decreases to 400 femtometers, the two protons lose all their kinetic energy, their speeds have become 0, they are repelling each other, and from there they should go back. But remember, to form a nucleus of these two nucleons, to form this 2H1 deuteron nucleus, they must come close to, let's say, 1 femtometer or less, only then they will be forming this. And at 400 femtometer itself, they have lost all their velocities. But we are still alive. Plants still grow. The activities on Earth is going on. So these protons are coming closer to each other. And they are coming in the range of this nuclear force, a femtometer. Even if at 400 femtometer, according to the classical physics, they cannot go closer than that. But they are coming closer to that. They are coming up to 1 femtometer or less, and they are forming this deuteron nucleus. And that is why finally few more reactions and we do have this hydrogen converting into helium. And energy being generated at the core and then radiated, and all planets getting that energy. That is because the nature is governed by the rules of quantum mechanics, the rules of quantum physics. That is why all this activity is there. That is why the planet is there. That is why we are there. That is why this recording is there. That is why this course is there. So I will be now talking of a little bit of this quantum physics with reference to hydrogen atom. We will start with hydrogen atom, and then we will go slightly for bigger atoms, and then solids in which you have several atoms bonded together, and then how that electron will behave there. So that quantum physics we will be talking